Okay, so we left off last week and we were talking about composite metrics. So let's review that real quick. Okay, so we were saying a lot of times we have multiple metrics that we care about, but a lot of times they're at odds with one another. So for example, we might care for an aircraft collision avoidance system about both the collision rate for it and also the alert rate for it. And ideally both of those are 0, but that's typically not achievable, and we typically have some kind of trade-off. So you can imagine each point on this plot is like a different design. And we said one of the ways we kind of understand the trade-offs between multiple metrics is this idea of Pareto optimality, where a point is Pareto optimal if we can't improve one metric without making another one worse. So we said this point is not Pareto optimal because we can make it better in both collision rate and alert rate. We have other designs that were better in both areas. But this point, for example, is Pareto optimal because there's nothing that we can do to make one metric better without making it a different one worse. And so then we said we have this thing called the Pareto frontier, which consists of all of the Pareto optimal designs that we have. But then these are all kind of equally good if we don't do anything else. And so we need to create these kind of composite metrics to allow us to select one of the points along this frontier. So we talked about some different composite metrics we can use. One was the weighted sum method, where we just give each of these different metrics a weight. So how much we care about alert rate versus how much we care about collision rate in a relative sense. And then we just compute the weighted sum of the values of all the metrics. So in this case, for example, if we said we care, maybe we wanted our weight vector to add up to 1, and so we gave 0.8 of the weight to collision rate, or sorry, to alert rate, and 0.2 to collision rate, then we would pick a point with the highest weighted sum. Okay, similarly, we talked about another type of metric we could use that used the goal distance. So we just wanted to figure out which point was closest by some distance measure to our goal. And typically we pick the goal to be something called the utopia point, which would be, in our case, 0 alerts and 0 collisions. We want to see how close we can get. So we compute the distance between all of our points and the goal, and then we pick the one that's the closest. And then finally we had one more metric where we're like, well, you could just combine them, and there's lots of different things you could imagine doing. But one option would be this like weighted exponential sum metric, which is essentially just kind of doing this distance thing, but with some weights as well. Okay, but I want to think again, just real quick about this weighted sum metric, because we're going to dive into it a little bit deeper now. And so you can think, so here I was just like, okay, it's 0.8, 0.2, that's how much we care about each of them. But how could we actually go about picking this? So you might say, well, you just ask an expert and you go up to them and you're like, hey, what is your weight between alert rate and collision rate? But that's kind of a weird question to ask people. And so you might be wondering, like, how do we pick the weights? And so a more normal thing would be to ask someone, well, which do you prefer? Do you prefer a design that has this alert rate and this collision rate versus this design that has this alert rate and this collision rate? Like, which of those two would you pick if you had to? And it turns out if we do this a bunch of times, we could actually elicit what their weight vector is without them having to like tell it to us or write it down. So we're going to do an example here. I brought the candy back. And we're going to try to learn a weight vector over some candy preferences. So, right, it'd be weird if I like came up to you and I was like, hey, I have these M&Ms, Sour Patch Kids, and Skittles. Please specify a weight vector for me that adds up to 1 and tell me the weight of how much you care about each of these. So instead, I'm going to give you pairwise queries for this. So again, we have, we're trying to learn this weight vector. We're going to require that it sums to 1. And we have 3 different candies that we want to understand the relative weighting between. So M&Ms, Sour Patch Kids, and Skittles. And we're going to do so using pairwise queries. So we'll do a little demonstration here. Again, we have this weight vector that we want to learn. And then W1 is how much we care about M&Ms relative to the others. W2 is how much we care about Sour Patch Kids. And W3 is how much we care about Skittles. And we said that we want all of our weights to sum up to 1. So what this plot is showing here is on the x-axis, we have W1. On the y-axis, we have W2. Just to make it easier to visualize, we're not visualizing W3, but if we know W1 and W2, since they have to add up to 1, we automatically know what W3 is. And what I've shaded here is any space that's not allowed to be a possible weight. So we already have the constraint that W1 plus W2 plus W3 is equal to 1. So this whole area here would be a region where they don't satisfy that constraint. So this shaded area is not allowed, and our weight vector could be anywhere inside of this unshaded area. Okay, so I need a volunteer who likes candy and has opinions about it. All right, first hand I saw. You can stay there if you want, but it will result in you getting candy, no worries. Okay, so what we want to do is I have this kind of final question or final pair of different candies. So all these bags have different amounts of the M&Ms, Sour Patch Kids, and Skittles. This bag has 1 M&M, 4 Sour Patch Kids, and 5 Skittles, and this bag has 5 M&Ms, 3 Sour Patch Kids, and 2 Skittles. And I'm going to give you at the end the one we think that you'll like better. But first we need to infer your weight vector over these various options. And so the first thing I'm going to ask you is this kind of first query here. So the 2 bags I have here, I realized that I didn't actually need to make candy for these bags, but I'll give them out after, so others can have candy. But one of these has 1 M&M, 3 Sour Patch Kids, and 6 Skittles, and the other one has 7 M&Ms, 1 Sour Patch Kid, and 2 Skittles. So if you had to choose between these two, which one would you pick? You'd pick A? Okay, great. So let's think about what it means that he picked A. Okay, so because he picked A, we know that if we prefer A to B, then we know that it must be the case that when we take the weighted sum with our weight vector for A, it's got to result in a value that's greater than when we take the weighted sum of our weight vector with the values in B. But I'll note this is an assumption that we're making. So we are assuming that in his mind he has this weight vector. Maybe he doesn't know about it, but that's how he's making these decisions. This is an assumption we are making. And that's how he's making decisions when we ask him his preferences. But this might not be true. Okay, this is an assumption that we're making, and this might not be the case, and we'll actually talk when we finish up about how we could potentially relax that. But given this assumption, we then know that if we preferred A to B, so we preferred 1 M&M, so 1 times W1, plus 3 Sour Patch Kids, so 3 times W2. Is that right? 136. Okay, great. And you preferred that to the 712. Yeah, okay, perfect. So it's 3 Sour Patch Kids plus 6 Skittles. So we know that that must be greater than 7 times W1 plus 1 times W2 plus 2 times W3. Okay, so we just expanded both of these sides. Okay, now I'm just going to do some algebra here. So multiply all of this out. And so I'm going to just kind of subtract everything over. So we get negative 6W1 plus 2W2 plus 4W3 is greater than 0. We also separately kind of had this constraint where we said W1 plus W2 plus W3 had to equal 1. We had to have the weight sum to 1. So what we can do is just manipulate this a little bit to say that 1 minus W1 minus W2 is equal to W3. And so I'm just going to insert that in here. So we get minus 6W1 plus 2W2 plus 4 times W3, which is, we're going to put in 1 minus W1 minus W2 is greater than 0. And so then we can continue to multiply things out. And eventually we're going to get that 5W1 plus W2 is less than 2. Okay, so that's all we did was just continue plugging things in. Okay, so it turns out this equation actually represents something that we call a half space. And what it means is that we can actually go back to our plot that we were making, and we'll see that if we plot this equation and fill in kind of all the values that satisfy this equation, that forms a half space, and these are weights that are possible for him to have. So let's go back here. So basically, I just programmed this to do that for us. So you can see, if you remember, we had 5W1 plus W2 less than 2. So if you think about it for a second, that's exactly this line. This line is 5W1 plus W2 is equal to 2. And then on this side is everything that satisfies that inequality, and on this side is everything that doesn't. Okay, so we've basically now kind of restricted the space of weights that are possible given his answer to that query. Yeah, question? A half space? Yeah, it's basically just something that is kind of in this form. It's just saying, like, if you have an inequality like this, it splits kind of the space of possible values in half, where half of them satisfy this inequality and then the other half don't. So what that looks like is like this shaded region here that we now added to our plot. On this side, it doesn't satisfy the inequality, and on this side, it does. Well, okay, it's half of like infinite space. That's why it's called a half space. I wouldn't focus too much on the word half. It's just like putting a plane through the space of possible, or a line through the space of possible values. Okay, all right, let's do the rest of them. So, all right, next bag has 6 M&Ms, 1 Sour Patch Kid, and 3 Skittles versus 5 M&Ms, 2 Sour Patch Kids, and 3 Skittles. B, okay. So what happened here is we didn't actually go through the math this time, but we would follow the exact same process to get a new half space. And so this time it looked like this. And we can see that we've kind of now further restricted the space of possible weights. All right, next one, 271 versus 622. A, okay, great. He's had time to look at them and study this. Okay, this is great. So we've further restricted it a little bit more. All right, number 4. A little tougher one.
I will go with 5. B.
With B, okay. Perfect, all right. So that's all I'm gonna ask you. So we could ask more, and then we could try to kind of restrict this even further, but we'll stop there. So now we know that this is your space of possible weights that's left. So there's different things you can do once you get to this point in this process. You can just kind of like take the center to pick a point. There's various options for how you would maybe pick a point now that you've kind of narrowed it down. I'm just going to kind of do it by eyeball. So 0.2, 0.6 looks pretty good. It's kind of in the middle here. And so then our third weight is going to be 0.2, so they add up to 1. So we're going to put those in here as our guess for your weight vector. So we're going to say 0.2 for this one, 0.6, and 0.2. Okay, and so then what we can do is take our final query and say that we had those 2 bags that we were going to decide between at the end, and it appears that if we use this weight vector anyway, the product of the weight vector with A ends up being greater than the product of the weight vector with B. And so we think you prefer A. How'd we do? All right, sounds good. So maybe we'll say after class, or actually I could probably just throw it to you. Let's give it a try. Nice. All right, extra points for that one. Amazing. All right, so that's how that works. Any questions on that? Yeah.
So when you wrote in all the weight vectors and like made more half spaces to like narrow down the space, like first I'm kind of wondering, did you guys choose these specific values to make it smaller each time? And then another one is like, can they conflict?
Oh my gosh. Okay, you literally just like touched on my exact two next points. So well done. Okay, so exactly what you just said. So in this case, we just pre-selected the queries. So I kind of just thought about it and was like, what would be good to ask? But you could imagine that we could probably do better if I like asked him the first one, looked at how this space changed, and then thought about, okay, well, what could I ask next such that it would give me like a half space that kind of maximally divides up what I have left. That's called active learning. And a lot of people do that. It's like a nice area of research, super interesting if you want to go into it. It's beyond the scope of this class, but that's like exactly along the path of what you'd want to do. And then to your second point of like what happens if it's inconsistent, so that's exactly right, that can happen. So let's say that instead we pick B here. We have no weights left possible. And what happened here is like we basically just got an inconsistent set of preferences. So some people might say that means you're kind of irrational. We were assuming that the human was perfectly rational, always optimizing this objective. But we could have been wrong about the form of the objective or things like that. It turns out like this can actually be pretty hard to do. Like if I gave enough of these and they were close enough together, you might kind of be inconsistent eventually. And so what a lot of people do is they will actually relax this assumption and instead compute a distribution over the weights and model the human's choice like in a probabilistic way. So that's what a lot of people do. And if you understood this, you have like an inkling towards understanding how like RLHF works. You may have heard for like large language models. There's obviously a lot more involved here, but this is kind of the general idea there. Okay, cool. So that wraps up metrics, and now we'll go into specifications. Okay, so we'll start with logical specifications.
We got a question.
Oh, we got a question. Yes.
Without probabilistic like measuring for inconsistent preferences, I guess like, do you mind? Is it possible like come up like a toy example for how you would go about doing that? Like, would you just like count the number of times that like they prefer something that like is in line with like your hypothesis one versus?
Yeah. So the question was, if we were to do that probabilistic version, is there like a simple example we could talk about? There's multiple things you'd have to consider. So the first is you have to model how the human is picking. So you're now no longer assuming that they're perfectly rational. They always pick the one that they prefer according to your model. And so what's a common thing to do is to come up with a model that, and there's kind of common models people use for this, that says they pick their favorite one with some high probability and they pick the other ones with some lower probability. So that's the first thing. You need to figure out how to do that. And then this problem of figuring out what's the consistent set turns into kind of like a Bayesian estimation problem. So using very similar techniques to what we talked about for Bayesian estimation for the parameter learning, you do something very similar in this case. Yeah. So now we'll get into specifications. I debated a lot whether or not I should say this, but I think I'm just going to. I have always found this really boring. So I'm going to do my best to keep this not boring. I didn't want to influence your thoughts on this, but it's important and we'll use it the rest of the course, so try to stay with me here. Okay, so a logical specification, it formally defines an operating requirement for a system using a logical formula. And all the logical formula is a precise expression that evaluates to either true or false. Okay, and so there's different ways that we can define logical formulas, different tools that we can use. One of those tools is something that we call propositional logic. And so propositional logic consists of these things called propositions, which are just statements that evaluate to either true or false. And propositions can be kind of decomposed or are created using these things called atomic propositions, which is just a proposition that cannot be broken down further. So I remember when I first started learning about this stuff and I heard about like atomic propositions, for some reason like the connection was never made in my mind to like atoms, but that is like the whole point. So it's literally just, it can't be broken down further. I mean, we maybe learned that atoms can, but in this case, that's kind of the way to think of atomic propositions. You take them and you use them to build up these like more complex propositions. So in this case, this is an example of a proposition. You don't need to worry about like what these symbols mean just yet. But this is a proposition, and then the things that kind of make it up are these atomic propositions. And in a second, we'll realize that what this basically says is that A needs to be true, and B needs to be true, and not C needs to be true. Okay, so what are the different things we can do with these propositions? There's these operators that we can apply to them. So one, kind of the simplest operator is not. So let's say that we have the proposition P. So again, it can be either true or false. And then not P is just the opposite of that. So if P is true, not P is false. And if P is false, not P is true. That's how to kind of read these tables. Okay, another operator we can use, now we're talking about, we have two separate propositions. We have P and Q. And we want to know, or we're using the operator called conjunction, which you can kind of think of in your mind as and. And so this will come out to be true if both P and Q are true. If there's any other combination, this will end up being false. There's also disjunction, which is kind of like or. So this will be true if either P or Q is true, or both are true. So P and Q true, it'll be true. If either or is true, and then the only time it's false is if both P and Q are false. Okay, there's implication. P implies Q. This is kind of like if-then. So if P is true, then it must be the case that Q is true. So that's kind of this first case here. In the second case, P is true, Q is false. So then that must mean that this implication is false. But if P is false, we don't really care about what Q is. We're not imposing any conditions there. And so it'll always just evaluate to true if P is false. Yeah.
Wait, sorry, for the disjunction, like, is it the same symbol as conjunction, or is it?
In the slides it is. Here, let me just, I think I can just draw on this. Good catch. Draw here. Oops. No. It should be that. So you flip it upside down. Good catch. Okay. Cool. Okay. And then finally is the biconditional. So this is like if and only if. And so this is only true if P and Q have the same value. So if P and Q are both true, this will come out to be true. If they're different, it'll be false. And if they're both false, it'll be true. If then, yeah, so this is saying, you can kind of think of it as like P implies Q. So if P is true, then it must be the case that Q is true. So in this case, P is true and Q is true, we'll evaluate to true. If P is true and Q is false, well, we just said if P is true, Q has to be true. So that means that it's going to evaluate to false. But that's the only condition we're kind of imposing. So we don't really care, like if P is false, we don't really care what Q is. So either case that will evaluate to true. Okay. So a quick example. Let's say that we want to express the following statement using propositional logic. We'll say if the agent is in a safe state, then the agent is not in a collision state. So when we want to do something like this, the first thing that we need to do is define some atomic propositions to build up our formula. So we'll start with this atomic proposition that we'll call S, and we'll say this proposition evaluates to true if the agent is in a safe state. And then it evaluates to, and then we have this other proposition called C, and that evaluates to true if the agent is in a collision state. Okay, based on what we just saw, can anyone guess which operator we should apply here? Yeah.
Implies.
Implies, yeah, exactly. So this is saying if, you can think of the implication as if then, like we were saying. So if the agent is in a safe state, then the agent is not in a collision state. And so that's just saying S implies not C. So I guess we also use the negation operator as well. Awesome. So that's propositional logic. There's lots of ways to expand on it. The first way to expand on it is something called first order logic. And first order logic basically just adds these things called variables, predicates, and quantifiers to propositional logic. So a variable is just an object in a domain. So you can think of it like maybe we let the variable x represent the state of an agent. And then a predicate is a function that evaluates propositions over variables. So all that's saying is, for example, we have maybe this predicate p of x that returns true if the agent is in a safe state. So if you remember, we said our variable x is the state that the agent is in. So when we apply p to x, we get true if that state was safe and false if it wasn't. And then maybe we define another predicate that we call q of x, that if x is a collision state, it will return true, and if x is not a collision state, it will return false. Okay, so an example here, we kind of can just take the formula that we had last time. I guess I used different letters than S and C this time, but we have the same exact thing we want to express. If the agent is in a safe state, then the agent is not in a collision state, so we just replace it with predicates and variables. Okay, then there's this last thing for first order logic called quantifiers, which allow us to evaluate propositions or these predicates over a collection of variables. There's different types of quantifiers. One is the universal quantifier, so it looks like this kind of upside down A here, and you can think of it as kind of saying for all. And so in that case, when you have this type of quantifier, it means that all variables in the domain must satisfy the proposition or the predicate that we put forward. And so an example would be if we want to say all states need to be safe states, then we can write all x, for all x, p of x, meaning for all of x, p of x must evaluate to true. Then there's also the existential quantifier, which is kind of this backwards E. And you can think of that one like there exists. So there needs to be at least one variable in the domain that satisfies the proposition. So for example, if we wanted to say at least one state is a safe state, we can write there exists an x, there exists a state such that p of x is true. Okay. Another example here. I don't know if we've talked about this grid world system yet, I don't really remember. But you can imagine we have this grid world where an agent can just kind of move around in these cells, and we want it to avoid ending up in this obstacle cell, the red cell there. And so our specification we want to express is for all states in the trajectory, the agent does not hit an obstacle. And so we're going to define some of these predicate functions. So we'll say O of x represents, or will be true if x is an obstacle state. And then we want to say for all states, the agent's not in the obstacle or does not hit the obstacle. So we can say for all x, not O of x. So for all x, whether or not it's in an obstacle state, does not evaluate to true. So just some examples on the left would be a trajectory for the system that does satisfy the specification, it doesn't end up in the obstacle, and then on the right, it does hit the obstacle, there is a state that hits the obstacle, and so it does not satisfy it. Okay. Another example, now let's add one more thing to this grid world, where not only do we want to avoid hitting this obstacle, but we also want to reach this green goal. And so we say the agent must reach a goal state and avoid the obstacle state. We'll use the same predicate we had before, so O of x represents whether x is an obstacle state, but then we'll add one more predicate here where we say g of x represents that x is in a goal state. So now we get to use both of our quantifiers, and just like we had before, we want to say that for all x, the agent is not in the obstacle state, and we have this additional requirement, which is that there exists an x such that x is a goal state. So we must have some x in our trajectory that is at the goal. So if we look at these two trajectories down here, very similarly, this one reaches the goal, and it doesn't hit the obstacle, so it satisfies this specification. And this one does not reach the goal. It does still avoid the obstacle, but it doesn't reach the goal, and so because we have an and here, the specification will evaluate to false. Yep.
So this would evaluate to true, for example, for the left trajectory. It would also evaluate to true if the goal state was like in the middle of the trajectory, right? It's just any kind of state.
Yeah, if it hit the goal and like kept going past the goal, is that your question? Yeah, that would still evaluate to true. In this specific problem, like whenever we show it in class, we call the goal and the obstacle like terminal states. So once it hits the goal, we specify that it just stays in there given the dynamics of the system. But that's true. If like it could keep going past the goal, it would still satisfy the specification. Okay, that's first order logic. Okay, so now we're going to keep kind of extending down this ladder. And the next thing that we kind of build on top of this with is something called temporal logic. And what temporal logic does is extend this first order logic to specify properties over time. So because we focus on sequential systems in this class, you can imagine that temporal logic is pretty critical for us. And the first type of temporal logic that we'll talk about is called linear temporal logic. And basically it specifies properties over linear sequences of states. So that just means kind of a set of sequences or a set of states that is just one after the other in time. There's three different operators that we'll talk about for this course. There's more operators for linear temporal logic that we mention, I think, as a side note in the book. But the three that we're going to care about, one is called always, and is written like kind of this square symbol, and P, which is our proposition. You can read it as always P. And if you're wanting to write it in LaTeX or in Julia, \square is how you get that square symbol, in case you're wondering. And what it specifies is that P must be true at all time steps in the future. Okay, I want to kind of explain these plots slowly because we're going to see a few of them. And I think what they're trying to convey is not confusing, but they can be confusing at first if you don't fully understand what kind of these axes mean. So what we're showing here is on the x-axis we have time, and then we have different logical specifications. So P is our proposition here, and then we have always P. And the way to read this is the blue dot indicates that it's true. If there's no dot there, it indicates that it's false. And so when we look at, for example, time step 1, we're looking at all time steps in the future. So all time steps from 1 on. When we look at whether or not it's satisfied at time step 7, we're only looking from time step 7 till the end. So we only care about what's in the future. So for example, when we say always P, well at time step 1, P is not true from time steps 1 through 4. It is true 5 through 10, but it's definitely not true at all time steps in the future. So always P is not going to be true at time step 1. At time step 2, P again, there's still some time steps in the future where it's not true. So always P is also not going to be true at time step 2, and so on until we get to time step 5. Now P is always true for the rest of the trajectory for all time steps in the future, and so we get that always P is true as well, and this will happen until the end. Yeah. I think we're like including 4 in the time that we care about. Yeah. The question was, is 4 also okay for always P? And then I guess one other kind of thing to mention is a lot of times when we're just kind of given a trajectory and we want to say, does it satisfy this formula? And so a lot of times we just will evaluate from 1 for all time steps in the future. Okay, and then the next operator we'll talk about is eventually. So this is kind of this diamond shape here, read as eventually P. If you want to know how to write that in LaTeX code, it's \lozenge. And basically what this is saying is that P must be true at some time step in the future. So not all time steps, but some time step in the future. So here's what an example plot would look like for this one. So now at time step 1, if we look at P, there is some time step in the future that it holds true. It holds true at 5, 6, and 7. So then eventually P is true at time step 1. Time step 2, same thing. There's eventually in the future, it becomes true. 6, eventually it becomes true. But as soon as we get to time step 8 and we look, there's no more time steps in the future where P is true, and so eventually P is not going to be true. Okay, and then the last one we're going to talk about, now we have 2 propositions here, and that's P until Q. So it's kind of this cursive U, read P until Q. And what this one says, it's kind of long, but it's not too crazy. It's just saying Q must be true at some time step in the future, so this one eventually has to become true. And P is true at least until Q becomes true. So let's see what this one looks like. So at time step 1, we have that, so we can check the first part, which is Q is true at some time step in the future. So at time step 1, yep, Q does become true at some time step in the future, but is P true until then? No, because P is not true at these couple steps, and so it's not true until Q becomes true. So for that case, P until Q evaluates false. Now let's move on to like time step 3, for example. Q does become true at some time step in the future, and P is true until then. So P until Q will evaluate to true. And then that's kind of holds for the rest of these until we get to time step 10. Now Q is not true at time step 10 or any time step in the future. There are no more time steps. And so P until Q is not going to be true. Any questions on any of these operators? Yep.
The part between P and Q on 6, would there be nothing on the bottom then?
Yeah. So the question was like, do we need these to overlap? Yeah, like P needs to be true at least until Q becomes true. So you need to have that little overlap there. Yes. Yeah. Okay, awesome. So now let's do another example. We've added one more thing to our grid world, which is this blue square. And we're going to say this is a checkpoint that the agent needs to go to. So our new specification is eventually reach the goal after passing through the checkpoint and always avoid the obstacle. So we're going to define some predicates here. We're going to say, I previously called this O, now I'm calling it F, so sorry about that. But F of S of T is, will tell us that the state at time T contains the obstacle. So what I was previously calling O of X. G of S of T says that the state at time T is the goal. And then C of S of T says that the state at time T is the checkpoint. And then we're going to use these predicates now to define our property. And so we get kind of this long formula here. And it's just kind of breaking down each part of this specification. So we're saying this first part is kind of that diamond symbol, which is eventually reach the goal. That was the first part. Then this next part, not G until C, that's saying don't reach the goal until you've reached the checkpoint. So then that's again, eventually reach the goal after passing through the checkpoint. That's what this part takes care of. And then we have, and always don't be in the obstacle. So, and always avoid the obstacle. Any other questions on that? Yep.
So if we wanted to allow trajectories which reach the goal, but then before reaching the checkpoint, but then they reach the checkpoint and then reach the goal, how could we modify this to include those trajectories? Since I guess that's what I initially thought the first, the sort of statement in natural language was referring to.
Okay, so the question is like if we want it to reach the goal, then reach the checkpoint,
right,
and then go back to the goal.
First, does it disqualify the trajectory as long as you reach the checkpoint and then the goal?
Okay, yeah. So you're saying like if you kind of follow the trajectory, you went to the goal, you went to the checkpoint, and then you went back to the goal, you want to say that that's like still okay. Let me think about it. I mean, my first instinct would be you might need to use signal temporal logic for it, but I'd have to think about that. It might be possible, it's just not immediately obvious to me how you do it. Okay. So here's an example of a trajectory that would satisfy this. We passed through the checkpoint and we reached the goal and we never hit the obstacle. Okay. Wake up, everyone. I told you I'd try to keep you with me, so here you go. All right, so that was linear temporal logic. We're going to move on to signal temporal logic. And what signal temporal logic allows us to do is to extend this linear temporal logic to real valued signals. Okay, so what is a signal? A signal is just something that kind of changes its value over time. So you can imagine we have time on the horizontal axis, the value on the vertical, and we just have some kind of points that represent this signal. And the signal, we just need to specify the time that each point was taken, and then its value at each time. It doesn't have to necessarily be at regular time intervals that we take these values. We just need a set of times and a set of values, real values. And so what signal temporal logic does beyond linear temporal logic is introduces two new things that we can do. One is it allows us to specify properties over a time interval. So say we have the time interval from A to B. So we could, for example, write eventually between A and B, P needs to hold. So that just means that this whole thing needs to hold only between A and B. And so what we're saying here is we have some time A, some time B, and we're looking within this time interval to evaluate this formula, eventually P. Okay, and then the second thing that signal temporal logic allows us to do is it allows us to map real valued signals to truth values. So it just kind of introduced this extra type of predicate function that we can use to map real values to a truth value. It has this form called mu sub c of our state. And all this is saying is we apply some function to our state and we check if it's greater than some constant value c. So it's just kind of another predicate that we have in our toolbox. So just to demonstrate that, we have some value c, and we're checking whether our signal is greater than that value. So it would satisfy it over here, but not over here. Okay, a white slide. Oh yeah.
Just to clarify so when we specify this dimensional property over A, B,
Yeah.
so do we mean that the eventually proposition is true for all times in A to B?
Yes.
So I guess that implies that, like, if we say eventually P, then P must be true at P. Just because if it wasn't at P, then like let's say that P was true at some C within A to B. Like naturally, I would say, eventually P within A to B. But I guess that's not the case here.
Yeah, that's a great question. So the question was like, if we say eventually, I think we had this kind of eventually between A and B. P, does that mean that P is going to have to hold at B because eventually needs to hold at every single time in between there? Do you know if that's true? Yeah.
I mean, as long as it holds at least once within A to B, then that would value because it's eventually.
Okay, so you're just checking when it starts at A, if it holds at A, basically. The eventually holds at A. Okay, so you're evaluating it kind of like at A. So like those plots we saw earlier where we had like time step 1 through the end, you could pretend like A was 1, and we want to check if it holds in that like interval from there.
And would that be the same for also be like always?
Well, always you just need them all. Yeah. So you need it to hold starting at the beginning. Yeah, that's a great question. Yeah.
Between time steps A and B.
Yeah, exactly. Yeah.
Just building on that, can you add open or closed set notation to A, comma B to like modify that condition?
Good question. Have you ever seen that before?
Say the question again.
Like, could you use brackets, I guess, instead of braces to do open or closed set notation on the time?
Short answer is yes, but I think it's a convention to do inclusive.
Yeah. So the question was like, could you have like these are like these closed brackets, so they're like including A and B. The question was like, could you have an open bracket here so that you don't include B, but you include right before it? And the answer to that was it's typically a convention to do it with these closed brackets, but you could do it in a different way if you want to. All right, let's go back here. Okay, white slide, wake up again. To wake you up and show you a table. So this table is from the book. I think kind of this is the crux of what we were trying to get to here, which is specifying properties for the various examples that we'll use throughout the quarter. So here's just 3 of the example problems that we'll use in the quarter. One is this continuum world example where you have this agent that kind of moves around in this square, and it wants to get to the green goal and it wants to avoid the red obstacle. And so just here's kind of what the specification looks like for that. So we want to say reach the goal without hitting the obstacle. So very similarly to the things that we defined earlier, we have a predicate for a state being in the goal, a predicate for the state being in the obstacle, and we say eventually goal and always not obstacle. Yeah, now that I'm thinking about, oh no, okay. I'm still thinking about this checkpoint question. I thought I had the answer, but never mind. Okay. Second one, in the inverted pendulum system, so we talked about that briefly in the previous lectures, where we want the pendulum to be upright, and so we want it to be specifically the angle between negative pi over 4 and pi over 4 radians. So anywhere in this green region and anywhere in this red region is not okay. So we define, we will specify our property as just keep the pendulum balanced, and we'll create this predicate B that will return true as long as the absolute value of theta is less than pi over 4, so that means it's in this green region. And then we just say that we want always B, so B always needs to be true. And then finally, for the aircraft collision avoidance problem, this one's a little more interesting because we get to use our temporal, specifying like a time interval. So if you remember, we said that we kind of assume that we have some time until the aircraft are going to collide. Specifically, we say that we have like 40 to 41 seconds before they might collide. And what we mean by they might collide means they've lost all of their horizontal separation. So at that point, we want to make sure that they have sufficient vertical separation such that they didn't collide when they got to that point. And so our property specifies that we want at least 50 meters of relative altitude between the time 40 and 41 seconds. So we want just at the very end when they've lost their horizontal separation to make sure that we have a big enough relative altitude. And so we will specify this predicate called S, which says that the absolute value of the relative altitude between the aircraft is greater than or equal to 50. And then our property is that we always want that to be true between 40 and 41 seconds. And you're seeing some Julia code over here. We're going to talk about how that works shortly. But essentially, he's created this very nice Julia package you can use to write these properties and evaluate them in Julia code. And you can see because Julia is so wonderful and allows us to use these Unicode characters, we can actually write the actual characters for these things. You have a question?
Yeah, so in the case of signal temporal logic, if we wanted to extend this to like fuzzy logic for whatever reason, would the truth values be just like other signals, or would they be like their own independent thing?
So the question was for signal temporal logic, if we were to extend it to fuzzy logic, what would the truth values be? So,
Yes.
I don't really know anything about fuzzy logic, so I don't think I can answer that one. Yeah. Any other questions?
I think actually the answer to that, but fuzzy logically it's just like a probability between 0 and 1 instead of roughly.
But there are ways to do probabilistic temporal logics, which might help address your fuzzy question.
Okay, a fuzzy way to address the fuzzy question. There's probabilistic temporal logics, so maybe that's an option. Thanks. Okay, all right, here we go. Wake up again. Important stuff that we're going to use for the rest of the quarter about to happen. Okay, so let's imagine that we have this signal here. And I'm going to talk about a really cool property of signal temporal logic. And for now, let's actually just focus on one portion of this signal. So let's just focus on one time step that we have. We'll call it t. And look at the signal value here. We'll call that st. And then we'll remember, we'll set our proposition equal to this predicate function that we introduced for signal temporal logic, where we say mu c of st, meaning that mu of st needs to be greater than or equal to c, if you remember. And then we're just going to define the function mu of st to be st, so it just returns st. So what we're really saying with this property or this predicate is just that the state, so this value here, needs to be greater than some value c. Okay? So, like I said, p will be true as long as our state, this value st, is greater than whatever constant c we specify. Okay. So I'm going to show you some kind of versions of this property or things that could happen. And I want you to pay attention to kind of like how you feel about them, okay? So here's the first one. So we satisfy the property. Think about kind of the feeling that you have right now. Okay, here's the next one. Here's another possible value for C. We're still satisfying the property, but think about what you're feeling right now. Okay, so if you thought about kind of your feelings, maybe when you saw this one, you kind of felt a little bit different than when you saw this one, right? Because here we were like almost failing, we like just barely made it. And over here we're like feeling pretty good. We're like not even really close to the failure. Think about this one as well. So here we're just barely failing. And then here, not even close. We like didn't make it at all. So these kind of things like feel different. And with these kind of binary yes or no properties, there's no way to really distinguish between this. Here they're just both satisfied or they're both not. But something that's really cool about signal temporal logic is it kind of gives us this value that we can use to quantify kind of these feelings that we might have. And so essentially what we do is we use this value called robustness. And I'm going to talk in a second about how exactly it's defined. But the way to think about robustness is it's some value. And at 0, or for values greater than 0, that will represent any trajectory that is a success. Any successful trajectory will map to a robustness value that's greater than 0. And then the ones that kind of feel more successful than the other ones will map to a higher robustness value. So you can think more successful, more robust, more far away from failing. For below 0, any trajectory that maps to a robustness value that is below 0 is a failure trajectory. And the more negative it is, the further it was from being a successful trajectory. Any questions on that? I haven't talked yet about like how we actually compute this value. Okay. So like I said, over here we're like feeling pretty safe. As we move over, we're almost failing now. We just barely failed, and then as our robustness becomes even more negative, we're like not even close. So how do we go about calculating this? So for that simple proposition we had, that was just like the mu sub c of s of t, we just calculated by subtracting c from mu of s of t. So remember when, for example, for this property where we just want st to be greater than c, we're just basically figuring out how far away st is from c. So that's kind of the intuition there. So we'll have a bigger gap here, and then a smaller gap here, which will result in that smaller value. Okay, but we don't just want to evaluate robustness for like this really simple formula. We want to be able to evaluate robustness for like more complex formulas, like the specifications that we use for our systems. So we'll talk about how to kind of extend robustness to these various operators that we might apply to those predicate functions. So for example, let's say that we have these propositional logic operators. So we're currently saying that P is going to be true as long as the state is greater than C. What if we want to know the robustness of not P? Nothing super crazy happens here. We're just kind of looking at the opposite property now. So we just flip everything over, and we just say that the robustness of not P is the negative robustness of P. Okay, now let's introduce one more property where we have Q is this predicate function where we need the state to be greater than D as well. And say we want P and Q. And so we need it to both be greater than C, and we need the state to be greater than D. So we've got both of these things that need to happen. And so the way we define the robustness here is we just take the minimum robustness between those two. So you can see that it was closer to not being greater than D. And so we're kind of taking this worst case. Because we need them both to be true, we're going to take the worst case between the two by taking the minimum. Okay, so you might be able to guess what would happen for if we have P or Q. Now we just need one of them to be true. So we don't have to take the worst case anymore, and instead we just switch the min to a max. And then finally we had this implies operator. For this one, I'm not actually going to go over how we get there, but there's an exercise in the book where you'll actually derive this. It's only like a couple steps, so I'd recommend checking it out. Yeah, any questions on this? Yeah.
So, I mean, this is like one case. So kind of like usually like we define robustness as kind of like from like what's your margin from like from your criteria. Does it mean you can have like an infinite based on like robustness? Kind of like can just go up and more. So like there's no like it's more like I'm thinking in my mind kind of like if you're putting a percentage of some sort or kind of like because you won't define like what's your margin, but it's kind of like you can go up and up and up. So it's kind of like how do you know what is a good robustness?
Yeah.
Fluctuate anywhere then.
Yeah, great question. So the question was like, okay, so your robustness is kind of how far you are from where you're trying to go. So it could just go up to infinity. Like, how do you know what's like a good number? Like you compute the robustness and you're like, okay, is this good, bad? The general intuition is that like near zero means you're closer to failing, but the scale of that could depend on your problem. So for example, sometimes your robustness might have units because, for example, like for the collision avoidance system, your robustness will typically end up being like how far were you, it's almost like a modified version of your missed distance, like how far were you from what we consider the collision region. So that'll actually have units of meters, and so you can understand like what that means and interpret it. In cases where you can't, sometimes robustness is still useful because as you'll see in the next few lectures, we can use it as kind of an objective. So for example, if we want to find a failure, we want to minimize the robustness. We want to get to a trajectory that results in a negative robustness because that allows us to find failures of systems. And for that type of minimization, the scale really doesn't matter. Good question. Any other questions?
When would you have a case of like the second one that you outlined here, where it's like P and Q? Because like, wouldn't you always want the smaller one for the more minimum value?
Let's say we had something that was like, I don't know, we need our aircraft altitude to be greater than 200 for some requirement, and we need our aircraft altitude to be greater than 500 for some other requirement. And so we just need both of those to be true, and then we have this case where we'll just take the worst case of those two requirements. Yeah. So the question was, when would we have some scenario like this? Yeah.
The P implies Q case too.
Sure. Maybe we say, like, okay, so the example we had earlier was like if we're in a safe state, that means that we're not in a collision state. And so if we kind of define like values for what it means to be in a safe state and not a collision state, then we could say how close we are to that property being true. Does that kind of make sense? Okay. So that was for the propositional operators. We also can extend the robustness to temporal operators. So again, we still have this P and Q, but now we're not just considering like one time step here. We're considering our entire trajectory. And for this example, we're going to say that C equals 0. And so for points in the trajectory that are above C, that proposition or that predicate is going to be true. And for points that are below C, it's going to be false. Okay, so now let's say we have this eventually operator that we want to define our robustness over. So again, we have that P eventually needs to be true. And so since we only need to be true at like one time step for this to be true, we get to take a maximum. So we're kind of picking the best case. So we're gonna end up picking this point here, the one that's like got the highest robustness by itself. And then you might be able to guess that for, so it'll be this one here. And then you might be able to guess similarly if we say that P always needs to be true, it needs to be true at every single one of these time steps. And so we're going to kind of take a minimum to take the worst case time step. So we're going to end up saying that our robustness in this case will be determined by that point. And then until you can derive this, or if you stare at it for long enough, you might be able to derive some intuition here, but I'm just going to give you the formula and say you can think about that one more if you want to. Any questions here? Yeah.
Question. When we write rho of S of t, I'm a bit confused how we can think of S of t, that argument as a time series.
So this is saying the max over all t that are in this, the robustness of that. So remember, if you remember before, we were taking the robustness of just a single time step. Now we're extending it, and so we're just taking the max over that robustness evaluated at each of those time steps. Good question. Okay. Okay, but there's still one problem that we need to solve, which is that later in this course, we're going to want to take the gradient of the robustness. So I kind of alluded to some optimization that might happen. But for now, you just have to believe me, we are going to want gradients. This is going to be useful. So there's still this problem that we need to solve, which is that all of these kind of mins and maxes that you saw throughout all these formulas I was showing you, they don't really play so nicely with this gradient operation. And let me explain why. So let's look back at this trajectory again and assume again that c equals 0. So we just, let's say we have this formula that we want between time step 1 and time step 10, p to eventually be true. So that's going to end up just being the maximum over all of the values of our state. And so in this case, it's equal to S5. Our robustness is just going to be whatever the value of state 5 is, the state at time step 5. And so let's think about what the gradient of the robustness is with respect to each of our states for each of our time steps. So if I change S1 a little bit, what is that going to do to the robustness? Yeah, so you're shaking your head. It's nothing. It's not going to do anything to the robustness. So the gradient with respect to S1 is 0. If I change S2 a little bit, same story. It's not going to do anything to the robustness because the robustness is just equal to S5. So the gradient's going to be 0 there, and so on, until when we get to S5, well, the derivative of S5 with respect to S5 is 1. So we do get something there, we get a 1. And then the rest of the way through, we're going to get more zeros. Okay, so this is kind of a problem. And this is just really not a very interesting or useful gradient because kind of like no matter what we do, we're just going to get something that looks like this until we get that one point where it kind of switches, the maximum kind of switches over. And so the fix for this is something that we call smooth robustness. And all that happens here is we replace all these min and max operators with something we call the soft min and the soft max. So the soft min is, it looks like this, and the soft max looks like this. There's this parameter W that kind of allows us to control how much or like how soft we're making this in a way. So if you think of what happens when W equals 0, well, when W equals 0, we get exp of 0, which is 1. And so we get 1 down in the denominator, and then we just get SI in the top. And so it's just going to approach the average of all of those points that we had in our signal. And then if W equals infinity, it's going to approach the true max or min. And so we kind of have this way to smoothly trade off between the two. Okay, so just to get some intuition here, I'm going to demonstrate this in a Pluto notebook. So what I'm showing here is that same signal that we were looking at, and I'm showing its gradient. So you remember, so when W equals 0, we don't have any smoothing applied. Actually, is that right? I didn't think about that. But okay, so we're applying no smoothing here, and you can see that we have kind of the same gradient that we had before. And then our robustness is just equal to that maximization term. And then as we increase W, okay, I think, is it like opposite of what I was just showing?
Zero is
Yeah. Okay. Well, anyway, so as you increase the smoothing, which is how it would work in the STL package, you can see that the gradient starts to kind of move from that kind of just one pointed version that we had, and it becomes kind of more smoothed out like this. And you can see that as this is going on, we approach the mean of the signal as our robustness value. So this is kind of close to the mean of the signal, whereas before we had the maximum of the signal. Yeah.
You have on the slides, if I'm not mistaken.
Yeah, I think it is opposite.
Which one is it? Like this version or the one on the slide?
I think it's kind of, let me get back. Yeah, I'll make a post later about that. I think we may have defined it in two different ways in the package versus in the textbook. So I'll let you know. Yeah, good question. Any other questions here?
Can you try to divide the lines going down so as you increase your W? Like your robustness goes down towards 0 and then reaches 0 at when you go to 10?
So it's not approaching 0, but you're right that it goes down. So the question is, why does the line go down? So we're trying to approximate the max function, because for this case, we were saying we want it to be eventually true, and so we're taking the maximum over all of our values. And as we kind of smooth out the max function, we kind of consider the contribution of the other values in the signal, and so we move away from the true max. And what it actually slides or kind of trades off between is it starts approaching the mean of all of the values. It looks like it's approaching 0 because the mean of all of the values is around 0. That's just a coincidence. It's actually approaching the mean.
Just to clarify,
Yeah.
just in the slide, it's.
Oh, it's just written wrong in the slide.
Textbook and the code, 0, 0 implies that you return the true min for the true max, whereas infinity, you get the mean. So as you approach infinity, you get closer and closer to the mean.
Okay, yeah. And actually, I think I probably even just wrote it wrong and said it wrong. Because if you look at the slide here, okay, so if we plug in infinity here, we're getting negative infinity, which gives us, like, I think this is just written backwards, right?
I think just the
way it's written. Yeah, okay. Yeah, it's just backwards in the slide. I'll make that correction. Thanks for pointing that out. Any other questions on this? Yeah.
I was just wondering why it was between 0 to 1 on the.
What?
Or I guess like I'm just
Oh,
taking
the
more to
gradient?
understand, like why is it supposed to like represent some kind of like probability thing?
The fact that it's between 0 and 1 is kind of. Okay, so it's just for like this particular formula. We said that mu of ST was equal to ST, so we want ST greater than C. So our robustness, and we said C is 0, so our robustness is going to be ST minus C, ST minus 0. So our robustness is just going to be the maximum over all of our states. Does that part make sense? And so in this case, our robustness is just S5, and we're thinking about taking the gradient. So if we take the gradient of this formula with respect to S5, we get 1. And so that's just where the 1 comes from.
There supposed to be like a summation in the numerator, because like on the previous slide where you define like, or maybe later slide where you define soft min and soft max, it just looks like the numerator and the denominator to me are the same. I don't remember exactly which slide.
Yeah, I'll try to find it. There is a subtle difference between the numerator and denominator. If I can get there. Okay, here we go. The numerator has this SI in it for both of them. Yeah, good question. Yeah.
You said it should be flipped?
Yeah.
Okay.
Sorry about that. I'll make that correction. And I guess kind of the way to think of it is like 0, no smoothing, we get the true emitter max. As we increase that value for W, more smoothing, we get, we go closer to the mean. Yep.
Example that you gave, I don't know if it's just a coincidence, but yeah, when you smooth it out all the way, it kind of like looked like it almost followed the signals, like distribution more or less. Like you can see there's like a little, it's kind of like a thing in the left half, and then it dips down. Is that just like coincidence, or is it supposed to just be like a bell curve? Or is it...
Well, so what's happening is it's like kind of following how much each of these is contributing to the max. It should be kind of, yeah. So we made it through what I wanted to make it through. Reachability, we're going to have as an advanced topic. I'm just going to click through these slides though because they're pretty, but I don't have time to talk about it, sadly. But it leads to like my favorite figure in the whole book. So if you get a chance to read it, even though it's an advanced topic and won't be on the quizzes, you should just check it out. All right, super cool. We can convert things that aren't reachability properties into reachability properties. You don't have to know any of this, but it results in these like automaton things that you can go through. I'll just keep flipping through it. So then we create this like product system, and this is like my favorite figure in the whole book. All right. Thanks for amusing me on that. If anyone wants to know more about it, I'm happy to show you those slides. I'll have candy at my office hours right now. Other than that, project 0 and quiz 0 due tomorrow, and have a good weekend. I'll see you next week.